So hello everyone, welcome to this presentation. My name is Marielle Van End. I'm from the Department of Material Science and Engineering at Seoul National University, and I've been using FactSage macroprocessing for developing process simulations for over 10 years now. The goal of this presentation is to give you the basic concept and syntax of FactSage macroprocessing to be able to create and run your own FactSage macroprocessing code. There will be another video which is dedicated to applying FactSage macroprocessing to a simple process simulation. But this video is more dedicated to basic concept and syntax itself of FactSage macroprocessing. So this presentation is intended for experienced users of FactSage, with also knowledge of basic concepts of computer programming, such as what are variables, or loops, or program flows. But you don't need to be an accomplished programmer because macroprocessing is rather easy to learn. So in this presentation, I will briefly explain what is macroprocessing and why it is useful for you. Then I will show how to create and run a very simple macro. I will go more into details and then explain the types of macro variables and functions available with macroprocessing. And finally, I will cover important macro commands. And throughout the presentation, there will be 3 live examples to illustrate the concepts and functions that are presented. So what exactly is macroprocessing? Macroprocessing is built in FactSage, so you don't need to install anything, it's already there. And it gives the users the ability to run equilibrium calculations as a background job. So whenever you have repetitive calculations, you can automate them with a macro. It was originally intended for internal quality control to check calculation results between 2 FactSage versions. So for that reason, the language and environment are not the most user-friendly, as it was not originally intended for FactSage users. Anyway, macroprocessing is very useful to automate repetitive calculations and is essential to develop process simulations using FactSage. So how does it work? Well, the user writes each step that he wants the macroprocessor to perform as a series of commands and functions stored in a macro file. The programming language is very similar to Visual Basic. The macroprocessor then interprets each command in that macro file and will typically load an existing equilibrium file, make changes in the reactants and conditions, calculate the equilibrium, save the result in stream or print out in Excel, and go to the next equilibrium file, and so on and so on. So macroprocessing is extremely useful to treat large and lengthy calculations that would otherwise be time-consuming and prone to errors if you're doing it manually. So how do we create a macro file? Well, macroprocessing will open only an existing equilibrium file. It will not create it for you or select appropriate conditions for you. Therefore, the first thing to do is to create an equilibrium file in which reactants, products, and conditions have been entered and stored. As a first example, we are going to create a simple equilibrium file with the following conditions. We have 3 reactants as follows, with 400 grams of Fe2O3, 400 grams CaO, and 200 grams of MgO. We will select the phases from the FACTPS and the FToxide database and fix the temperature at 1500 degrees C. And then we save the equilibrium file as equilib1.equi inside the folder C example. Okay, so we go to the equilibrium module. So I'll now open FactSage and the equilibrium module to do so. So I'm using currently the FactSage Workshop version 8.1. So I will make a new reaction. Yes, so I clear the system. And then I will enter the 3 reactants in the reactants window. So we have 400 Fe2O3, 400 CaO, and 200 MgO. Then I will check that the units are correctly set. So I can see already here that the quantity is in mole and I want them in grams. So I have to change that. So I'll go to the units and then check the temperature. It's in Celsius, so it's okay. The pressure is in atm. That's good. And then my quantity, I will change it into grams. Okay. And then I click OK. I will also make sure that the option initial conditions is not checked because I'm not interested in the initial conditions of my reactants, so I remove that. Then I will go to the data search to select the database. So here the FactPS is already selected, and then I will select FT oxide as well, and then check that no other databases are selected. So I'm good. I'll click OK. And then, because I've selected my reactants, change the units, check the database, can go to the next window to select the products and the final conditions. So we will select the gas phase and the pure solids and all the solutions available there. Okay, and then I will, on top of that, limit the slag A to a single phase. So I right-click on the plus here and then choose single phase. Okay, so that will simplify a little bit my writing for later on. And then lastly, we enter the reaction, the final conditions, the reaction temperature here as 59 degrees C and the pressure at 1 atm. Okay, then we need to save this equilibrium file so that the macroprocessor can access the reactants and phase selection and equilibrium conditions that I have just entered. So we go to the menu File and Save As, File, Save As, and then we browse on our computer to look for the folder C example. So I go to C and then look for example folder here. So if you don't have it, then you can create it with the new folder option here. So I will open C example and then I will write the name. So I want to have name equilib1. Okay. You don't have to add the extension .equi because FactSage will do it for you. Okay, so you can save it here. It will prompt for a comment. You can enter a comment if you like. For me, it's not important, so I'll just leave it like this. So we have finished creating the equilib file that the macroprocessor will access. So now we can create the macro file. Basically, that will tell the macroprocessor what to do. So the macro file has the extension .mac and is editable with any text editor, such as Notepad or Notepad++. I personally prefer Notepad++ because it allows syntax highlighting and has useful plugins. In this presentation, all the macro files are edited with Notepad++, with which I have highlighted some of the macro processing commands. So there are three basic commands. The first one is open filename.equi. So it will open an existing equilib file named filename and load the reactants and conditions that are stored in the file. Note that the extension .equi must be included. The second command is calc. This will perform the equilibrium calculation with the given conditions. So it's similar to pressing the button calculate in the equilibrium module. And then the last one is save filename. So this command allows to save results in several formats, like text, Excel, or even create streams. The extension .text, or Excel, and so on must be included at the end of the file name. So let's use our equilib file to create a macro. So I will open Notepad++. I get a blank page and write the commands to open, calculate, and save the results in a text file. So by default, the macroprocessor is direct to the FactSage installation folder if the file path is not specified. It means that it will look for files and save files in that folder, which is typically cFactSage or cFactSage WS, even though you set the myfiles directory in the equilib module to a different folder. It will still look in the FactSage installation folder. So we need to indicate the full path to our files in the macro file when they are not stored in the FactSage installation folder. Okay, so we need first to tell the macroprocessor to open the equilib file. So I use the command open, and then I give him the file name with its full path. So C \example \, and then the name of the equilib file. So equilib1, and then I don't forget the extension .equi. Okay. So this command will open and load all the reactants, phase selection, and the calculation conditions that are stored in there. Then I will ask him to calculate equilibrium. Okay, with the command calc. Okay, nothing else needed. And then we will save the results of that calculation using the command save, and then I will tell him where to put it. Again, if I want them in a C example, then I have to specify the path. So C example \, and then let's save it as example1.txt. So that will store the results into a text file. Okay. After that, I have to save that on the hard drive. So take save as, and then I'm already in C example. If you're not, you can go to the C example folder and then create a name. So this is my example one. Sorry, example one. And then I have to add the extension .mac for FactSage and for the macroprocessor to know that this is a macro file. Okay, and then I usually change the save type to all types to make sure that Notepad++ is not adding the .txt extension or any other extension to my file name. Okay, so I have the example1.mac. I can just save it. Okay, so in my case, because I have kind of like set up a .mac file with this option, most of the FactSage commands are actually highlighted in blue. Okay, so if I make a typo, I can see directly that the command has not been highlighted. Okay, so we have created our first macro file. So now we are ready to run it. Let's see how we can do that. So to run a macro file, there is only one place in the Eclipse menu to do so. So it is from the reactance window. In the file menu, there is a submenu macro processing where the command run is located. You can actually see two run commands. The first one is a shortcut to the last run macro. So if you have never run a macro before, it will be empty, like shown here. The second one allows you to specify a different macro. So we select that second option, and then when you select that option, there is a new window which opens asking the name of the macro that you want to run. So you can type the name here, or you can select Browse to locate the macro file. There is also a shortcut to the macros directory here, located in the FactSage installation folder. They contain many macros to illustrate specific conditions or functions of macro processing. Once we have selected the macro files, we can click OK, and then the macro will then start immediately. So let's do this with the Eclipse module. So I go back to the Eclipse module. So here I'm in the main menu window, and then if I go to the file, I will see that I don't have this macro processing option here. I have to go back to the reactance window. Okay, so if you go to file, then the macro processing menu is there. And then I have to run. I already run something before, so it's already there. But if I want to select something else, then I have to go to run macro. And then go to browse, and then go to my C example folder, and then select my example1 macro, which I just made. Okay, so I can click open. The name will be changed here. And then once I click OK, the macro processor will start. Okay. So during the execution, you can see that the macro processor will take control of Eclipse. So the Eclipse file is opened by the macro processor and then switches between menu windows. And it will execute the commands written in the macro file one by one. There is a new window which appears on top of the Eclipse module. This is the macro status window, which is here. Each command that the macro processor has executed is printed there. So as you can see, the macro processor has already completed the execution of the macro rewrote. It was very short. We can see the name of the macro that was executed here, and then the instructions that we gave him in the macro file. So open Eclipse 1, calc, and save the results in a text file. So we can also go to the C example folder to check the example1 text file, which is created here. Okay, so this file contains basically all the results of the equilibrium calculations in the same format as in the results window of Eclipse. So as you can see also, there is no compiler or debugger with macro processing. Each command is evaluated or interpreted at runtime. In most cases, the macro processor will terminate with an error when an error is encountered. For example, I can make a typo in one of the commands here, so I save it again and run it again. So you can see that now, because I ran a macro before, there is a shortcut to that to that macro. So if I click on this, it will start automatically, immediately. And then you see that because of the typo here, the microprocessor does not recognize the command here, cal. So it stops there and saying that it does not understand what to do. And then it stops, it terminates the macro at that time. As you can see here too, in this macro processing, macro status window, there are 5 buttons on the left side. You can see their functions in the presentation file. So now they are grayed out because the microprocessor has already completed this very short macro. Well, during runtime, these buttons allow to prematurely terminate the macro using the quit button here, or pause the macro using the stop button, followed by either terminate or go to resume the processing. And then there's also a button to hide the equilibrium window during processing and show the equilibrium window during processing. So we have just seen how to open an existing equilib file, or calculate the equilibrium and save the results in a text file with this very simple macro. So we can now look at how data values can be stored using variables and how they can be manipulated in the macro code using built-in functions. So like any programming language, macroprocessing has variables to hold data values as well as built-in functions. So there are 3 types of variables in FactSage macroprocessing. They are identified by the symbol preceding their names. So the first type is the user variable and is identified by the symbol % at the beginning of the name. The variable is created by the user and its value can be modified by the user. The second type is a system variable, which is denoted by the symbol $ at the beginning of the name. This type of variable cannot be created or modified by the user. Only its value can be accessed. The third type of variable is the thermochemical variable, which is created by equilib after loading an equilib file or calculating an equilibrium. This type of variable cannot be created or modified by the user. Only its value can be accessed. So let's look more in detail at each type of variable. So the first one is the user variable, which is identified by the symbol % at the beginning of its name. So the type of value to be stored in this variable does not need to be defined. So it can be a string, a character, an integer, or a double. And the type of value can be changed anytime in the code without the need to reset or convert the variable. So there are 9 pre-declared user variables denoted person1 to person9, which are already created. So any values can be readily allocated to these variables without the need to declare of a declaration. In addition, the user variable person tier is reserved to reset the default FactSage directory. So the path defined in this user variable will tell the macroprocessor where to look and store files when the path to a file is not specified. Any other user variable has to be declared by the statement variable or dim. The declaration is done only once, and the variable must have a unique and non-ambiguous name. A value is allocated to the variable with the sign equal with the space before and after, which is optional. The user variable can be defined as a one-dimensional array or a vector. It is declared by specifying the size of the array between round brackets in the variable statement. So values are allocated by specifying the entry position in the array between round brackets, 1 by 1, or as a block like shown in this example. So I created the %temp variable which is an array of size 5 with 5 entries. And then I assign the value 10 to the first entry, 100 to the second entry, and then I can also several values at once by specifying the range of entries here. Macroprocessing also supports a 2-dimensional array, like matrix, with the total number of columns and rows of the array specified in between round brackets at the declaration. The value allocation at each entry is done by specifying the column and the row in between round brackets, then followed by the value to be stored. Once you declare them, the array can be redimensioned with the command redim. Note that this command basically will erase all the values stored in the array before the redimension. System variables are the second type of variables available in microprocessing. They are identified by the symbol $ at the beginning of the name. They are built-in and denote system values, such as time, date, directories, and so on, and which cannot be modified by the user. The value can be printed or stored in a user variable. For example, $time is the current time, $date is the current date, and $macfile will give you the full name of the current macrofile in use. The last type of microprocessing variable, and probably the most important, is the thermochemical variables, which are identified by the symbol $ at the beginning and at the end of the name. They are generated by the equilib file and during the equilib calculations. They refer to extensive property values, or names, mass, mole, concentration, activity, and so on, for elements in solutions, product species, and also solutions. And they're essentially any information that you can get from equilib will have a matching thermochemical variable to be retrieved by the microprocessor. As for system variables, they cannot be modified by user. However, the value can be printed or stored in a user variable. There are more than 150 thermochemical variables available in microprocessing. So I have selected only a few that are relevant to the type of applications that we are doing. So they are listed in the table here. The notation follows a specific structure and look quite complex at the beginning, but it gets easier as you use them. The first letter after the symbol $, the uppercase E, indicates that the variable is an equilibrium value created after an equilibrium has been calculated, so after the calc command. The second uppercase E indicates an absolute value, and the uppercase T, the temperature. So this thermochemical variable represents the equilibrium temperature from the equilibrium. So you could replace the uppercase T by uppercase H to have the absolute enthalpy, or uppercase G for the absolute Gibbs energy, and so on and so on. You can also have property change when the initial conditions have been defined. So this thermochemical variable here gives the delta enthalpy by replacing the uppercase E here to uppercase T, get the delta. And then H for enthalpy instead of T. To designate an element, we use the notation lowercase e here, and followed by the element code number I. We add the uppercase N to get its name. So this thermochemical variable will give you the name of element with code number I. Then we can change uppercase N by lowercase m to designate a mixture, and lowercase j to designate the mass, to get the mass of the element I inside a mixture. And here we specify the mixture with the code number K for the mixture. For species in solutions or pure compounds, we designate them by the lowercase s. Okay, so we still have the uppercase E to designate the equilibrium value, and then s, lowercase s, to specify a species. Then we can specify, we can give like uppercase N to get its name, lowercase g to get its mass in grams, uppercase W to get its concentration in weight %, lowercase m to get its mole, and lowercase a to get its activity. And then lastly, we have to add the code number for the species J has to be entered to specify which species you want to have the information. For solutions, the syntax is very similar. So the lowercase s for species is replaced by a lowercase m, for mixture or solution. And then we can use a similar symbol here to designate the mass, like G here for the mass, and uppercase N to get their name. And then we specify the code number for the solution, which is K in this case. So the main difficulty here is to identify the code numbers I, J, and K for elements, species, and solutions. So they are specific to each equilibrium file, as the numbering is based on the elements in the system and on the phase selection in the equilibrium file. If you add a new element or if you select or unselect a phase, then the whole numbering will change and the codes will be shifted. So how do we find these code numbers? So the code numbers can be found from the species selection table in the plot menu in the equilibrium module. So the plot is only available when at least 2 calculations have been performed. So you can make calculations at 2 temperatures, for example. It does not really matter as long as both calculations succeeded. So I will show you how to do with equilibrium. So I'll go back to my menu here and I will enter a second temperature to get 2 calculations here. The temperature you choose does not really matter as long as it will give you an answer. And then I press calculate. So this will give me 2 pages, and then in the output, the plot menu will be active because I have at least 2 points, okay? So I go to plot results, and then I have the results processor here. And I'm actually not interested in making a plot here. I'm just interested in generating this table, okay? So the number that you see here is the numbers for the species, okay? Each species in the gas, in the solutions, and then in the pure solids. And it stops here. So for the solutions, the gas phase is always 1, even if the gas was not selected as a possible product. And then you just need to count and follow the order in the table. So the slag A will be number 2, spin A will be number 3, and so on and so on. For elements, we need to scroll down and check the numbers. For example, we can already know or find the thermochemical variable to get the amount or the mass of MgO in slag. So this will be the answer, so $E because it's an equilibrium value. And then we want the species, so we use small s to designate the species. Then we want the mass, so we use lowercase g. And then the code number for MgO in slag, we look in the table, and then it's here. MgO in slag A is 15, so we place 15 here. And this thermochemical variable will return the mass of MgO in the slag. And then, for example, if we want to know the total mass of slag A, in this case, then we use this thermochemical variable. So $uppercase E for equilibrium value, underscore, small m for mixture, small g for mass, so the mass of mixture, and then we need to find the code number for the slag, which is gas was 1, slag was 2. So the slag is number 2, so we place the 1 here. So for the elements, we go down the tables, and then we have to count the order in the table. So starting from 1. So iron is 1, calcium is 2, magnesium is 3, and oxygen is 4. Okay, so you have to be really careful here because the numbering stops at the last actual species here. So the number that are listed here should not be considered. These are not the code numbers. For the solutions, you have to start counting again. So 1, 2, 3, 4, 5. For the elements, you have to start counting again from 1. 1, 2, 3, 4. Okay? So for example, if you want to know the mass of iron in slag, then we have to use this thermochemical variable. So $E for an equilibrium value, underscore, E to designate an element, not a species, and then we want iron. So the code number for element iron is 1, then underscore, and then we want the iron from a mixture. So we use small n to designate a mixture, G to get its mass, and then we want the slag, so we have to find the code number for the mixture slag, which is 1, 2, number 2. And then again, for the mass of Mg in slag, it's similar, except that the code number for Mg is 3 instead of 1. Okay. So alternatively, you can also use a little macro that automatically lists all the code numbers for elements, solutions, and species from a given equalifier and text file. So I will show that in the next video with the application of a simple processing machine. The thermochemical variables for species are built like one-dimensional arrays. So you can access and copy more efficiently a range of values at once, instead of copying each species one entry by entry, one by one. So in the first example here, I'm copying the concentration in wind percent of species 1 to 10. So it will group all this into 10 entries and then copy them in the first 10 entries of this user array, instead of basically doing it one by one. So I can just do it one shot, 10 entries at a time. You can also have non-matching positions between the thermochemical variable. So it doesn't have to be 1 to 10 and 1 to 10. It can be different entries between the variable and the thermochemical variable. So the only important thing is that the size of the range that you take has to be identical at between the equal sign. And also you can copy, as shown here, for the activity of the species, all the values related to species at once by omitting the code numbers. So if you don't specify any number here, you can also remove the brackets. The microprocessor will understand that you want to have the activities of all the species at once. And then you can copy them directly into a user array like this. But the size of the arrays must match on each side of the equal sign. So you have to know in advance how many species there are in the equilibrium file so that you can create the array with the correct size. So macroprocessing has also built-in functions that are identified by the symbol $ at the beginning of the name and an argument in between round brackets at the end. So we have $ at the beginning and brackets at the end. So these functions allow manipulating strings, formatting outputs, calculating mathematical expressions, and so on. So the most useful one is the $mat function to calculate mixed mathematical expressions, including the operators plus, minus, division, multiplies, and squares, and so on. So this function is actually needed even to make simple calculations, like 1 plus 1. You will have to make 1 plus 1, write 1 plus 1 inside the arguments here. Other useful built-in functions include the minimum and maximum functions and the absolute function. The arguments can be numbers, strings, user variable, system variables, and even thermochemical variables, but not another function. Okay, so I always say other functions also interesting are $minimum, $maximum, and absolute to get min and max functions and the absolute functions. Since FactSage 7.0, the user can create its own functions and procedures, also called subroutines, in the macro file. They are very convenient to structure the code and to perform particular tasks and avoid repetition of commands within the program. But they are not presented in here in this video, but you can find more about them in the FactSage macroprocessing manual. So let's look at the example number 2. I'll close everything here. I will not write all the code because it would take me forever. But we're going to look at each command, and after that try to run it. So this example will illustrate variables and functions. So first, to make a comment in the code, you can use a double slash here. So the microprocessor will ignore the text written after that double slash until the end of the line. So I'm starting with the declaration of several user variables. So the declaration must start with the statement variable, or dim. It's not case sensitive, so you can also write it in lowercase. Then you can list one or several user variables separated by a space. And you should not forget the percent symbol at the beginning of each name. You can have several lines of variable statement. And you can mix arrays and non-arrays within the same declaration. And once declared, you can assign any value to the variables. So here I have assigned the number 1600 to the variable %temp and the string dummy to %dummy. You can use the equal sign if you use, or you can, but it's optional. You can leave it out. So if you use the $sign, the equal sign, sorry, so make sure to have a space before and after it. Otherwise, it may give an error or not assign what you actually expected. Next, I'm resetting here with this command the default FactSage directory to C example using the reserved variable %dir. So %dir, even though it's a user variable, does not need to be declared. It's created by default. And thanks to that variable, I don't need to specify the path to the files that are stored in C example anymore. The command open equilib1 or save example 2, if you remember our first example, we needed to specify everywhere we need to look into there, but now you don't need to specify it anymore. It knows where to look for. So after opening the equilibrium file and calculating the equilibrium, I'm storing equilibrium calculation results into the array, person array, okay, which I declared here with 6 entries. So it has a size 6. So I need to specify in which position or entry of the array the value has to be stored using the number in between round brackets. So this will designate the first entry of the array, person array. So in the first entry, I will store this thermochemical variable using the corresponding variable here. So $E, uppercase E, underscore, uppercase E, uppercase T, and then $sign. So this will store or give me the equilibrium temperature from the equilibrium calculation. In the second entry, I will store the mass, which is the uppercase G, of mixture, which is the lowercase m, with code number 2, which is the slag, as we saw in the PowerPoint presentation. In the third entry, we have the thermochemical variable with a lowercase s, so it designates a species, then lowercase g, which designates the mass, and then the code number 15, which was for MgO. So here we ask for the mass of species number 15, the mass of MgO in slag. And then in the fourth entry of person array, I'm storing this thermochemical variable, which is a species with code number 15, MgO in slag. And I'm asking its concentration in 8%. Okay, so this will be the concentration of MgO from the slag. And then the fifth entry, I have a small e here, so this is for element. And element number 1 was iron. And then I want its name, which is the uppercase N. And then finally, in the last entry, I will store again the element number 1, so iron, but I want the gram for like a lowercase g from the mixture, so a lowercase m number 2. So this will designate the mass of element iron inside the slag. Then I'm saving the results, like in the first example, in example2.txt. I don't need to specify the path here because of the %dir declaration. And lastly, we calculate manually the concentration in weight percent of the MSGO in slag by calling the Dolomite function. So to calculate the weight percent of MSGO, I will need the mass of MSGO in slag and then the total mass of slag, and then divide these two numbers. So I need to call the Dolomite function to make that mathematical expression. Okay, so I'll multiply by 100, get array number 3, which is the grams of MSGO in slag, and array number 2, which is the total grams of slag. So I will get the weight percent of MSGO in slag. Okay, so let's now run, and then I will store the value into %m. So let's now run this one. So I have to go back to the reactants window, go to File, Microprocessing. I don't want to run this again, so I have to find the second option, Run Macro, and then Browse to get my example number 2. Selected, Open. Then the name has changed here. You can also just type it in if you want, and then click OK, and it will start immediately. Okay, so you can see here the flashing a bit more. It lasted a little bit longer, and you can see here in the macro status window what happened. You can make it bigger if you want, if I can manage to do it. Yeah. So it seems here it has created 2 variables or 3 variables that I wanted, and then it starts assigning values inside each variable. Change the directory here, open the equilibrium1.equi, and then calculate, and then starts getting the information from the thermodynamic variable. So here it finds 1500, 712 for the mass of slag, 19, almost 20 for the mass of MgO, and this is the weight percent of MgO. This is the name of element number 1, which is iron. So inside the array, you can mix numbers as well as strings or just words. And then this is the mass of iron, element iron inside the slag. Then we save, and then here you have the mathematical expression here. So you can see here it interprets everything here and changes the values of each variable inside the mathematical expression, then calculating the mathematical expression, and then storing it inside the variable, and so on. And this, of course, here is identical to here. So the calculation is matching. So we have seen the different types of variables and how to obtain the results of an equilibrium calculation in various formats and important built-in functions. So now I will introduce important commands to create loops, control the flow in the code, and interact with Excel, and read and write to worksheets, how to change reactants, phase selections, and conditions using the command set, and how to save streams with the command save. So I will go through the syntax of each of these commands, and then we will illustrate them with an example at the end. So the first command is step. So using the following syntax, %var, which is a user variable, then step, and then a value. So step must be written here in uppercase letters, very important. So these commands will add value to the user variable %var. It's in fact identical as using the Dolomite function, which is written here. So this has the same effect as doing %var equal, then calling the Dolomite function, calling again the same variable, plus adding the value here. So value can be a positive or a negative number. It can be also a system or thermochemical variable, as long as it's a number. And if value is omitted, then value becomes 1 by default. So if you just write %var step, the 1 is used instead of 0. Loops are very useful in programs because it allows repeating some instructions a certain number of times. So in microprocessing, only the 4 type of loops that runs for a preset number of times is implemented. So the syntax is as follows. The loop starts by defining a loop variable, which must be a user variable here because it will change value. And then we have an initial value, and a final value separated by 2. And then we can also have an increment to be specified with the step comment. So if you omit that part, then it will assume 1 by default. Then we enter the instruction to be repeated under that statement. And after that, we finalize the loop by writing the variable again plus the label loop, so LOOP, in all uppercase letters. So the loop is initialized with first value, meaning that a loop is always executed at least once with this first value. And when the microprocessor arrives at the end of the loop here, the loop variable is incremented by the increment value or by 1 if it's not specified, and compared to last value. So if it's smaller or equal, then the instructions here in the loop are repeated, are executed again. If not, then the loop is exited. So nested loops, meaning a loop inside a loop here, so we create another loop inside here, are permitted as long as the loop variable, so this variable must be different. Note that here, to and step and the loop here must be written in uppercase letters, otherwise it will not work. There are also several commands to control the flow of the program execution. A marker and the go-to statement can be used to immediately jump to another part of the program indicated by the marker. So the marker location in the code is indicated by the mark statement, followed by a user-defined identifier like word here, like a label. So the marker cannot be located inside a loop or a conditional statement. The marker can be located before or after the go-to statement to make a backward or forward jump. And you can have more than one marker in the code, providing that they have different identifiers. And you can have multiple go-to statements associated with the same marker. And a go-to statement can be used to exit or break a loop before termination. The label end indicate to the microprocessor the end of the code. So all commands that are written after the label end are ignored. A go-to statement can be associated with the end label to create a jump to the end of the program, so it means quit. A conditional if statement can be combined with a go-to jump with the following syntax. So in the conditional expression, so this one, if bar upper and value, we typically use a variable, which can be a user variable, a system variable, or thermochemical variable, is compared to another entity, which can be here a number, a string, a variable, or even a function. And the jump to the marker word will take place if the condition is true. So the relational operators here that are available include equal to, less than, greater than, not equal to, less than or equal to, and greater than or equal to. So you can have 2 or more expressions can be used in the conditions, which are connected by the logical operators and or. And then in this syntax, go-to must be written in uppercase letters. The if, else conditional statement allows to perform different actions for different decisions. So the syntax for microprocessing is shown here. The first line starts with if, followed by 1 or more condition expressions, like with the same kind of syntax as we saw in the previous example. And then the block of code here to be executed just follows this line, and the line here has to fin by then. And then if this condition is true, then the block of code here will be executed. In the condition expression, there's As we saw before, then a variable, typically a variable, is compared to another value, which can be also a user or system or chemical variable or number or string or even a function. So the relational operators here are identical to previous examples. So equal, lower, greater, and so on and so on. So you can also compare two or more expressions in the conditions connected with the logical operator and an or. You can have one or more else-if statements to be added to specify a new condition if the first one or the previous ones are false. So they are optional, and the syntax is similar to the first if statement. So you put else if, then you put the condition, followed by then, and then the line codes. The else statement here, so you just write else, which is also optional, is specified to use a block of code to be executed if all the previous conditions are false. And then the end of the if-else-if conditional structure must be indicated with the label and if. In microprocessing, nested ifs are not permitted, so you cannot start a new if block inside the code here. So if you need this kind of structure, then you have to be more creative by using multiple ifs and else ifs, or and or operators, or use goto and markers to tackle more complex conditional structures. And importantly too, the first then labeled here has to be in uppercase letters in here. Another flow control available in macroprocessing is the do case. It is functionally identical to an if-else, else-if-else structure. Both specify a series of conditions and an optional fallback, which is the else, if none of the conditions are true. So with do case, all the conditions are dependent on the same variable, which is defined at the first line here, just after the do case kind of marker here. And it can be a user variable or a system or even a thermochemical variable. So the do case conditions are evaluated in the order they are listed in the structure. And in macroprocessing, the conditions can have different expressions. So the do case variable can be compared exactly to a given value using the syntax here. And or it can be compared to a range of values separated by the two, and to a condition using relational operators where operator is equal to or greater or smaller and so on. So do case acts on the first true condition in the structure. So even if several conditions or even several cases apply, only the first one will be executed. So once a condition is true, then the microprocessor executes the statements or the block of code which is written under the case statement here. Then the do case is exited. And then the keyword and do here is required to mark the end of the do case structure. So as for the if, else, if, and if structure, then nested do case are not permitted. So you cannot start a new do case even with the different variables inside the block there. And in addition, variables cannot be used here. You can only use values. So this is like everything for program flows and steps and loops. Next, I will talk about an important feature of macroprocessing. It is the ability to interact and transfer data with Excel worksheets at runtime. So this feature is enabled with via object linking and embedding, so OLE. So you can have up to 9 simultaneous OLE links, named OLE1 to OLE9, created between macroprocessing and Excel worksheets. So data can be transferred from and to Excel worksheets, meaning that you can read and write anytime during the macro execution. So this feature is ideal to store inputs and outputs, organize and plot results in an efficient way. So there are several commands associated to OLE. The principal OLE commands are listed here. So the first one consists in the creation of the OLE link with the worksheet. So it should follow that syntax. So first we have the label OLE with a number 1 to 9, between 1 and 9. Then we enter the Excel file name with its extension and full path, if not in the person dir directory, followed by the sheet name. So the number n here must be attached to the label OLE. Both XLS and XLSX Excel files are supported. So you can use quotation marks to enclose an Excel file name if the file name contains space characters. So the same applies if the sheet name has a space. You have to use quotation mark for the name. So note that if the Excel file is not found, the macroprocessor will create with the specified Excel file name along with an empty sheet with the specified sheet name. And similarly, if the sheet name is not found in the existing Excel file, then it will create an empty sheet with the specified sheet name. So when the macroprocessor executes this command, if the Excel file is not yet open, then the Excel program is launched and the Excel file is open in the foreground. If the Excel file is already open when the command is called, then the macroprocessor will use the open version of the file, even though some changes have been made compared to the saved version. So next is the command to clear the entire sheet or specific range in the sheet. So this is interesting, basically to erase previous calculations to make sure you're not mixing up two calculations together. So first, the OLE link should be specified to know in which file and which sheet the operation is done, followed by either cells or clear to clear the entire sheet, or range, and then the range reference, A1 to C5 with a semicolon there, and clear to clear a specific range. In OLE commands, there are two reference styles for cell address of Excel. So the A1 style with a combination of a letter and a number as displayed in Excel, which is more common and straightforward. And then the R1 C1 style, which is made up with the letter R followed by the row number and the letter C followed by the column number. So as you know, a range is defined by the reference of the upper left cell, for example, A1, and the reference of the lower right cell, for example, C5. And then you separate them, these two references, with a column. So the command for reading a value from Excel and storing it in a user variable is as follows. First, we define the variable name where the value will be stored. Then we follow by the OLE label and its number that will tell in which file and which sheet to go. And then the label read, tell them like we want to extract the value from Excel, and then the cell address. Okay, so we can give this, as I said, in the A1 style, so here it would be B5, or the R1 C1 style, which is R5, so row number 5, column number 2. So these two cell addresses are identical. So you can choose whatever you prefer. So similarly, the command for writing a variable to a cell in Excel is as follows. So first, the variable name containing the value that we want to pass to Excel. Then the OLE label plus the number to know where, in which file and which sheet to store it. And then the command write to say that we want to transfer it to Excel. And then the cell address, where basically the value will be written. And again, here you can choose either the A1 style for the reference or the R1 C1 style for the reference. This is the same. And finally, the command to close and save the worksheet. So the OLE label and its number here to know which file and which sheet to close, followed by close and save. So this command will close and save the Excel file and clear the OLE link. So after that, you cannot use this OLE reference anymore because that has been erased. Okay, so the only way would be to go back to create a new link with the same N. So there are several other OLE commands not listed here to perform mostly changes in cell and text appearance. So they are listed in the macro processing manual of FactSage if you are interested in them. Additionally, you can use arrays to write and read from an Excel worksheet. So for example, I have created a one-dimensional array here, a variable with person vector with 4 entries, and then a two-dimensional variable called person array with also 4 entries, but structures with 2 rows and 2 columns, like a matrix. So we can, of course, fill these variables one entry at a time by specifying the variable entry, so vector first entry A1, second entry B1, and so on and so on. So, however, this will become slow when the number of Excel connections becomes large. So a more efficient way is to call the entire vector, meaning all its entries at once. So to do that, we basically omit the position. So this will basically call the entire vector and specify a range in the worksheet to write to or read from. So, and in addition, in the case of one-dimensional array and horizontally adjacent cells in Excel, only the first cell of the range needs to be specified. So for example here, person vector has 4 entries. I specify which file name and sheet name I want to, and then read, and then I'm just selecting one cell. So the macro processor will automatically include horizontally adjacent cells when the entire 1D variable is called. So here, the macro processor will read the values of the 3 horizontally adjacent cells and fill them inside the variable entries. So basically, B1, C1, and D1 will also be included in the vector. Okay. Similarly, for writing a one-dimensional into a worksheet, so the whole vector can be called, and only one reference can be given. The microprocessor will write the other entries into horizontally adjacent cells. So the next cells will be filled with the entries, with all the entries of the vector. So note that this only applies for data arranged in cells horizontally in the worksheet. If the data are stored vertically or to be written vertically in the worksheet, then you need to specify the full reference by using, first reference and second reference. In case of 2D variable, like a matrix, using, for example, the array here, you always have to specify the entire range inside of Excel. Otherwise, everything will be written horizontally. So the last commands I will present in this video are the set and save commands. So the set command is used to redefine reactants, initial amounts and conditions, database and phase selections, final conditions, and so on that are initially defined in the equilib file. So the most important set commands are the command to change any initial reactants amount, temperature, or pressure using the following syntax. So first, the label set and reactant, then the reactant number here. So this is the position in the list of reactants. Then the label mass to change the mass, or we can also change the temperature, pressure, changing the labels here, mass by T or by P, and then the new value to be used. Then we have the command to change the final conditions. So first the labels set and final, followed by, for example, uppercase T for temperature, but you can also apply alpha, beta, the pressure, or the product here, Z, then followed by the new value to be used. And then the command to change the estimate value in case of target calculations. So first, the label set estimate, followed by T, or P or V or alpha, depending on the target calculations, and then the new values to be used. So note that changes made with the command set are not saved in the equilib file. So when you reopen the equilib file, the original reactants, phase selections, and Gaussians, any conditions will be restored to what it was inside the equilib file. So there are other set commands available, but they need to be used with caution, as they will change the phase selection and the code numbers in a way that can be difficult to address. So I usually prefer to add all possible reactants and select the products manually and save them in the equilib file so I have a better control of the phase selection and can anticipate the code numbers beforehand. But you can add a new reactant with the command set reactant add. And then you can specify the chemical formula. In case of a stream, the stream name has to be entered in between square brackets. So the new reactant is added at the end of the list. So the phase selection, especially for the compounds and the solutions, might not be automatically updated. So additional steps might be necessary to modify the phase selection after adding a new reactant. You can also delete an existing reactant with the command set reactant del, then specifying either the chemical formula or the stream name if it's a stream, or the reactant number, meaning the position in the reactant list. You can modify the species and phase selection by using the command set select, followed by the type of product that you want to modify. For example, gas for gas species, compound for all compound products, including gas, pure liquid, and pure solid species, solid for only pure solid species, liquid for only pure liquid species, and solutions for all solutions, followed by the symbol plus to select, minus for unselecting, or exclamation mark for making metastable. So this command here will select all the species or solutions that are available. So here, specifically for the gas, it will select all the gas species available in the equilib file. You can also make species selection based on a specific database. For example, here, set select solid plus FT oxide will select all the pure solids from the FT oxide database. And you can change the solid bar gas, compound, or solution to apply selection to a specific database to different type of products. This selection can also be made for a specific species from a database or solution. So set select solid plus FT oxide MgO will select the compound MgO from the FT oxide database. So for solutions, you can also use the uppercase letter I, as shown here, to set the solution with possible two-phase immiscibility. So here, the solution slag A from FT oxide database can be set as possible two-phase immiscibility using this command, set select solution I FT oxide and then hyphen slag A. And then you can also use plus or minus to select and unselect everywhere here. One disadvantage of using set select here is that it does not follow the default phase selection defined in the equilib module. For instance, the default excluded species marked with the X inside the equilib module from the database selection in the compounds, and the default I or J option for the solutions that are applied automatically in the equilib module are not applied when using set select. So all these default settings then must be specified individually in the macro code. For this reason, it's recommended to check carefully the phase selection with set select, or even with adding a new reactant, before you calculate the equilibrium to make sure that the phase selection is okay. And finally, the command save. So we have already seen that this command can be used to save results in various formats, such as text or Excel file. It's also used to save the computed phases in a stream file. So the syntax consists in first the label save followed by the name of a stream. So there should be no space in the name here. So here we write save and then the name of the mixture file, including the extension .mixed, followed by the label gas to save all the gas species inside the mixture file, or the label solids to save all the solids in the mixture file, or the label solutions to save all the solution in the mixture file, or you can also save a specific solution in a stream by specifying the database nickname and the solution nickname separated by a hyphen. This will save the FELQ solution from the FT miscellaneous database inside the mixture file. And in case the solution has the possible phase emissivity option activated, the IOJ option, then the solution nickname must be appended with the pound sign here, followed by the number of the immiscible phase to be saved. Okay? So a few other useful macro commands are listed in this table. So I have already shown the / command to make a command line. There is also the command rem, so rem, which has the same function, except that the command is also printed in the macro status window, while the previous one here is not. The command hide allows to hide the equilibrium window in the background during the macro execution, while the command show will make the equilibrium window visible in the foreground during execution. So these commands have the same functions as their corresponding buttons in the macro status window. And then the command pause will pause the running macro until the user clicks in the macro status window the button go to continue the macro or stop to terminate the macro. It's a very useful command when debugging, as it allows to check the commands and the variables value that have been executed so far, as they are printed in the macro status window, and then also to examine the Eclipse file in use if the command hide has not been called. So let's look at a simple example to illustrate the concepts of what we learned. So we will use the equilibrium from the two previous examples, so equilibrium1.equi. We imagine that the material defined as a reactance is being heated at a rate of 50 degrees Celsius for a given duration. So we want to have the initial temperature, the feed composition, and the process duration stored in Excel file. And we want to print out in Excel as well the amount of slag, the amount of iron in slag, and the slag composition as oxides with temperature in the Exxon sheets. So the idea is to enter all these process conditions inside Excel so that the code in the macro file does not need to be changed every time we want to be, or if we want to change the conditions. So we can create the Excel file and the worksheet containing the input data. So this will give us basically the names of the Excel file, the sheet name, and also the position, the location, the reference, the cell addresses inside the Excel. So I've already created the Excel and worksheets with the input data to be faster. So these cells indicated in red in the worksheet sheet 1 have to be read by the macro. And then we will print out the equilibrium results in the same Excel file, but in worksheet sheet 2. So we want to arrange the results in such a way that one row here corresponds to one temperature. During the execution of the macro OLE commands, it's important not to interact with the Excel application, so we will see why with the example. So you should not click in a cell in the active sheet, or go to another worksheet, or even open another Excel file when the macro is running. So these actions will interfere with the embedded link, and the macro may start reading or writing in the wrong cell, worksheet, or file. So the best is basically to leave Excel alone during the execution. So let's look at the macro file to achieve that. So I will go to my example number 3 here. So I have the command hide to start with. So this will basically hide the equilibrium window so we don't show it flashing here. I have created a list of variables. So here I've put everything into the same line, but you don't have to. You can make several lines if you want. And then each of them is separated by a space. And then you need to have, for each of them, percent symbol in front of this. Okay? So here are just the normal variables, and these are 2 arrays with size 4. Then I'm resetting the default FactSage directory to my C example, as we show in the example number 2, using %dir. Okay, so you have to use quotation mark if you have a space in the path. And then here I'm creating the OLE link. So the first one is OLE 1. It's up to you. You could use OLE 3 or 7 or 9. It's up to you. Then I have to give the file name. Here example.xls is stored inside C example, so I don't need to give the full path. If I want to use it from somewhere else, then I have to give the path. And then I have to designate which sheet. It should be sheet 1. So we can go here and open the example file and go to sheet number 1. The name here of the sheet has to be the same as name here. Otherwise, the microprocessor will create a new sheet and empty. So you won't be able to read anything. And then here, I will create a second OLE link, OLE2, with the same Excel file, but a different sheet, sheet number 2. Okay? And then, because sheet number 2 will contain my outputs, I will clear the entire sheet to make sure I'm not keeping the calculation results from the previous simulation. Okay? So I have created my 2 OLE links. So now I can start basically reading the input conditions from Excel. Okay, so I have created variables basically to store most of the things. So I created a variable temp here to get the temperature. So now I want to get the value. So the value is stored in the sheet 1, so I have to use OLE1 to designate that worksheet. And then I want to read. So I gave him to read, and then I'm giving in the address. If you remember, there's 2 styles, so B1 or R1C1 style. Here, it's just more convenient because Excel already gives you the address here to use this style of writing rather than the other one. So we do the same with the duration. So this is B2, and then the amount of Fe2O3 for the reactants, which is B4, and then the amount of CaO, B5, and then the amount of MgO, B6, and all of them are stored in different variables. Then I have created 2 variables here, which will basically store the position, the column, and the row for printing out. Okay, so this is one, and I'm setting them up here to start. So it basically means that when I will print out the results, I will start at the first column, so the A column, and the second row, number 2 here, but in the other sheet. Okay, so we know from the problem statement that we have to repeat the same calculation for a certain amount of time, a certain number of time. So I will do that instead of writing the code like 15 times or so. I will make a loop, and the loop will go from 1 to the duration. So the duration here is a condition, so it could be 5, but next time I might want to make it 10 or 15. So I can just change the value in here, and then automatically it will be changed here when the macro will read the value from the Excel file. Okay, so you can have like a last value being actual variable. And then in this loop, well, what I will do, basically open the equilibrium file, equilibrium1, and then we're going to overwrite the reactance amounts with the amounts that are inside the Excel file one by one. So first set reactant 1 inside the equilibrium. 1 was Fe2O3. So I'm giving now the variable Fe2O3, which basically is linked to B4, okay? And then we do the same with the second reactant, which is CO, and we give the new value, being the value stored into B5 of the Excel file. And then MgO, we do the same for the reactant number 3. Also, we have a different starting temperature than the one stored in the equilibrium file, so we can also override that using this command, set final T, and then using this value, which is coming from Excel as well. Then I do the calculation with the new reactants amounts and the final temperature. And then we can save the results or save the output into different streams. Just to show how to create streams, basically. So this command save will create a stream named gas.mixed inside the folder. And then this label will say that all the gas species will be stored in that mixture. And then we can also create another stream called solutions. Then we have to specify the dot mixed extension to say that it's actually a mixture. And then here specify I want all the solutions from the equilibrium calculation stored in there. And then here, lastly, I want to create a mixture file called slag with extension .mixed. And then in that one, I want specifically to have the slag A solution from the FDoxide database. Okay, then after that, I start basically writing into the Excel, one value by a time. So the first thing is to have the temperature, because it will change, so we need to kind of like monitor what's the temperature. So I will take the temperature that I've put into the final temperature and then write it into OLE2. So now it's not OLE1 anymore. I want this into the outputs. So now I have to direct this to OLE2. And then I'm not reading, I'm writing. Okay, so it will take the value from temp and store it into OLE2 at this address. Okay. So I use this writing here because now it will change at every time the loop is run. And then because I cannot increment a letter, like to use the A1 style, I have to use the R1 C1 style. Because these are numbers, it will be easier to increment automatically. So the first one would be R person row. So when the command arrives here, the microprocessor will change person row with whatever value it is now, and person colon. Okay, so at the first loop, this will be R2 C1. Okay. Then I have to move, so the column has to change so that I'm not writing in the same cell over and over. So I give colon step. So this will add 1 to the variable colon. It was 1 at first, now it's going to be 2. Then I'm going to ask for the name of the slag phase to make sure that the code number 2 I'm using it is what I think it is. So I'm going to try to get the name of that solution and store it in the user variable, and then use that user variable to write it to Excel. Because of this command, you cannot use a thermochemical variable directly to write or read into Excel. So first I have to store this thermochemical variable inside a user variable, and then use the user variable to store it into Excel. Okay, so you have to have a kind of like intermediate variable to go from a thermochemical variable to the Excel file. Okay, so I get this, I put it there, and then I use this variable to write it there. And then I write it just next to it. So the column has been incremented, so now I'm in the next cell. And so on. So then I move to the next cell. And now I stored the mass of the mixture number 2 inside this variable. Then I use this variable to store it, to write it to Excel. It's always the same thing, except that basically col has been incremented. So it's essentially the cell next to it all the time. Then I move it to the next cell. And then I get the name of element number 1, which is iron here, store it in this variable, use this variable to write it, and so on. And then I move to the next cell, get the mass of iron from the mixture number 2, which is from the slag, and then basically use that variable to write it to the cell, and so on and so on, and move to the next column. Now I want to have the name of the species with the code 12 to 15. So I'm interested in basically writing all the species from the slag into the Excel file. So if I go there, and if you remember how to do this, do 2 temperatures and calculate to get the plot function working, and then go to the table. And I want to have the concentration of these, basically of these 4 species inside the slag. So I need to have these codes 2, 12, 13, 14, and 15. And then because they are adjacent, I can basically call the block here. Okay, 2, 13, 14, 15. So that's what I do here. I'm calling species name of several species at once. So small s for species, large N for name, and then I'm giving the range 12 to 15. So this will take these 4 names at once, and then I'm storing it into my user variable slag species, which is basically an array of size 4. Okay, so this is an array of size 4, and this is an array of size 4. And then I will take this array and write it directly into the Excel. And then here, because everything is horizontally aligned, I can just basically give the first cell where I want to start printing. And then the other 3 entries of the variable will be printed next to it horizontally. Okay, so this one R1 C1. So I want to write it in the first row all the time, so that it's kind of like title. Then I'm doing something similar to get the composition. So here I ask for the name. Now I'm asking for the actual concentration in weight percent. So I've changed, the only thing I've changed is basically the capital N to capital W. Okay, but it's the same codes, for example. And then I'm using a different variable here, /com, which is also an array of size 4. And then I'm basically printing that one time into OLA2 at this address. And again, I'm just specifying the first cell, and then the microprocessor will print out the 3 other entries into the next 3 cells automatically. Okay, and then we have a small function here for the if goto. So we have if first, and then we have our operation condition. So we try to compare the variable temp to 1650. So when temp becomes greater than 1650, then we go to N, so it means that's weight quit. Then I'm preparing the variables to be incremented to be ready for the next loop. So the process is hitting by 50 degrees per step per minute. So here I use %temp step 50, so that will add 50 to temp. Then I also increment 1 to step to row, percent row, using step. So it means that I'm going to the next row to be able to print, and then I'm resetting the column to 1. So it means that I'm starting a new line first column. And then this is the end of my loop. So %1 will be incremented by 1 because I haven't given any increment value. I then compare to duration. So if %1 is less than duration, then it will do that again. And if it becomes greater than duration, then it will stop the loop. And then just after that, we have the end kind of marker. So this will basically tell the microprocessor to stop. Okay. So let's try to run that. So again, we have to go to the reactance window to start the macro. Go to File, Macro Processing, and Run Macro. We don't want to run example 2, we want to run example 3, so we have to go to the next option. We can either just type 3 there, or go to Browse, and select example 3 without any problem. Okay, once we are done, we can OK, and then the microprocessor will start. Okay, so you see that your Excel file is still there, but now you have no control over it. So now the microprocessor is basically reading and writing every time you call the OLE function. Okay, so it has red values here. You can see what it did inside the code. So here we have much more, so it's going to be a bit more finished, but it's basically doing this. So we open there, read all the values here, so you can see whether you read everything correctly. If you change the values correctly, and save the picture file and what kind of values you put there, and write it every time for each loop. Okay, so I can also close that Excel file, and it will start also automatically. I'll just close that. So if I run it again, and the Excel is closed, it will open automatically Excel as well with that file. If it's open and I made some changes in the sheet 1, and I didn't save it, it will still use the open version, so with the changes, even though it's not saved. Okay. I can also illustrate what the hide command is doing. So if I now command this line, means that the hide command is not going to be executed. Okay, and then you can see the difference in terms of like effectiveness. So it's basically every time it's kind of flashing the equative line. So that's why it's sometimes better to have this hide command so that you don't have this flashing thing when the macro is running. Okay. I can also show you what the pause command do, which why it's very helpful. Basically, I will usually pause after a calculation is done. Again, don't forget to save anytime you make some changes in the macro file, and then run it again. And you can see when it hits the pause command there, it will stop and basically wait for an action, whether you want to stop, so you're not happy about what's happening now and then you want to stop it, or you say it's okay and I will just want to continue. So when it's on pause and the hide command is not called, so it means that you can see your equative file here with the results of this, because it's just after calc, with the results that has just been calculated. And the interesting thing is that you can also check what's going on in there, okay, in the equative file, in the reactance, to see, for example, that the changes that you made here with the set reactance actually have been considered, okay, correctly. And for example, if you made some changes with the set select, so if you made changes in the product or solution selection, that the changes are actually happen the way you want them to do, okay. And then if you're happy, then you can say go. Also, an important thing that you should not mess with when you use this is basically starting to do this clicking thing. Okay, because if you start clicking, I should probably just remove the pause first, because it's always stopping at the wrong moment. It starts basically messing with the sheet, and then you can see here it basically starts writing and reading in the wrong place because you interfere with the OLE links. So now everything is kind of like screwed. Okay, So that's why it's very important not to start like clicking in places that you should not during the execution. So it's important not to click in there, because if I start clicking there, even like it's just going to give you an error, or it will start like seriously reading and writing in the wrong position. Okay, so it's really important, basically, not to interact with Excel. You can still see and look, but you should not change a sheet or open another Excel file or click in the cells when it's running. Okay, just leave it alone. That's the best. This is best. Okay, so let's go back to here. So we saw that. So this is all from my side. So I have covered the most important aspects of FactSage microprocessing. So now it's your time to try it out. So if you have any question or would like to know more about other commands, so you can have a look at the FactSage microprocessing manual here that you can access from the info, the information menu, and then there's microprocessing, and then there's manual, summary, and example that are available here. And of course, you can always contact me here. So I give my email address. If you have questions, you can always send me an email. So thank you very much for listening. And yes, if you have any questions, don't hesitate to contact me. Thank you very much.